This is a pre-built version of the application. So let's go ahead and run the server and two clients. And this will be the server, and this is the first client, and this one the second one. And I put the test data that we will be using in this file. So this is for decimal test data, and this is for hexadecimal test data. We'll be using two curves for that. The SEP256 K1, which is used by Bitcoin, and this other curve. So we'll start with running in ASCII mode and in base 10. And we'll use this generator point and this secret key. And Bob will use this curve with this generator point. And let's say we have this key. So in ASCII mode we will not be able to enter text, so it should give an error if we do that. So let's enter ASCII. So we'll try to send this ASCII message to Bob, and we'll choose this ephemeral key, and let's first try to sign it with an invalid key. So Bob realized that the message was not signed with Alice's private key. He received the signed message and calculated W1, U1, U2, and the point P. Took P of X, which is V, and checked if V is congruent to R in mode N, and determined that this message was not signed by Alice. So now let's go ahead and send the same message with the same ephemeral key, but this time sign it with Alice's private key. So here we go. The message was signed with Alice's private key. So same thing, he calculated W, U1, U2, and the point P, and took V and checked if it's congruent to R, and this is the value of R. Now let's say that Bob wants to send this ASCII message, and let's use this ephemeral key, and his key that we chose was this one, 9. So here we go. Alice determined that the message was signed with Bob's private key. And actually Eve can see all the communications. So she has the domain parameters that Alice is using, so the curve and the generator point. And she also has the domain parameters that Bob is using, also his curve and generator point. And she can see communication originating from Alice and from Bob. But in order to sign those messages as being Alice, she needs to solve the ECDLP, the elliptic curve discrete logarithm problem, and compute his or her private key D or ephemeral key. And same thing in the case of Bob. To sign messages as being Bob, she needs to solve his elliptic curve discrete logarithm problem for his curve and compute his private key D or ephemeral key. Now, before proceeding with the code, let's do a quick summary. So we have it set up here where Alice wants to send a signed message to Bob. So she selects the domain parameters, the elliptic curve, coefficients A and B, and prime number P, and the generator point A for the cyclic group with prime order N. And then she picks the secret key D between 0 and N and calculates the public key uppercase B, where B is D hops from the generator point A. And she sends A, B, P, N, and the generator point uppercase A and the public key uppercase B to Bob. And then when she wants to send a message, a signed message to Bob, she starts by picking an ephemeral key such that the ephemeral key is between 0 and N, and then she calculates the point R, which is ephemeral key hops from the generator point A, and then she sets lowercase r to the x coordinate of this point R, and then she calculates s, which is congruent to h of x, or the hash of x plus d times r multiplied by the inverse of the ephemeral key, and all of that in mod n. And she sends the message x and r and s to Bob, so the signed message, and Bob has domain parameters for Alice, and he has her public key uppercase B. So he starts by calculating W, which is congruent to the inverse of S in mod n, and then he calculates U1 and U2. So U1 is congruent to W multiplied by h of x in mod n, and U2 is congruent to W multiplied by R in mod n. And then he calculates the point P, which is U1 multiplied by the point A plus U2 multiplied by the point uppercase B. And finally he validates the signature. So if the x coordinate of this point is congruent to R from here in mod n, then we have a valid signature. Otherwise we have an invalid signature. I will start by creating a new project. And here we will have one package which will contain the server code, and another one for the client code. And we will need to do JSON, so we'll pick up this jar from here. And go to properties and Java build path, and I put the test data that we will be using in this file. Now on the server side we will have two classes, a server class with a main method and a server thread class, which will extend from thread and on the client side we will have four classes, a client class with a main method and a client thread class, which will extend from thread, and this class will represent the elliptic curve, and this one a point on the curve, and we will start from the server side. And here we will have three instance variables, a server and a buffered reader and a print writer, and we will initialize those in the constructor, which takes in a socket and a server and uses the socket to initialize the buffered reader and the print writer. And here this will be the port that the server will be listening on, and we will have a set of server threads for the different clients that this server is interacting with, and a get method for that set. And this method does message forwarding, and we will call it from here to forward messages from Alice to Bob, or the other way around. And we will start by instantiating a server and a server socket given the port number, and indicate that Eve is eavesdropping on all communications. And while this server is up, we will pick up or accept connections from clients and dedicate a server thread for each connection, and put that server thread in the set of server threads, and call the start method on the thread, which will end up triggering a call to this run method when the operating system decides to do so. So if the JSON message contains domain parameters, then we indicate that. Otherwise, if it is a signed message, then we indicate that for Eve to sign messages as being that person, she needs to solve the elliptic curve discrete logarithm problem and compute the private key D of that person that signed the message, or the ephemeral key for that message. And this should do it for this class. And next we'll do the client side. And those are the x and y coordinates for a point on the curve, and we will initialize those in the constructor, and those are two get methods. And this indicates if we are running in ASCII mode, and this is used for testing purposes, so we don't do any hashing in this mode for the message, and this indicates what base the user enters their numbers, so either decimal or hexadecimal, and this is the name for this user, and this is the name for the other user. And we keep track of the domain parameters that are used for this user, so the elliptic curve and the generator point, and the domain parameters for the other user, also the elliptic curve that the other user is using to sign messages with, and his generator point, and also his public key point. And also we keep track of the private key for this user, and if we are ready to send and receive messages. And those are get and set methods. And here we have a buffered reader instance variable and a client instance variable, and we initialize those in the constructor, which takes in a socket and a client instance, and uses the socket to initialize the buffered reader instance. And for convenience, we will define those and we will keep track of the curve coefficients A and B, and the prime number P, and the number of points in the cyclic group N, and the cofactor H, which is the order of the elliptic curve over N, and we will initialize those in the constructor. And we will have those get methods and this toString method that will print out y squared is congruent to x cube plus the value of a, x, plus the value of b in mode the value of p. And here we indicate if we are running in ASCII mode and what base the user enters their numbers in, and we instantiate a client and a socket, and for the purpose of this tutorial the server will be running on localhost and listening on this port number, and we instantiate a client thread and call the start method on it, which will end up triggering a call to this run method when the operating system decides to do so. And this method does pickup and processing of user input. Given the base, they enter their numbers in, and we will call it from here. Now we want to make sure that the elliptic curve entered by the user is not singular, so it satisfies this expression for a cube plus 27b squared is different than 0 in mode p. And this method will do that. And it will be called from here. And we display this to the user in case we have a singular elliptic curve. So this method picks up the values of a, b, p, n, and h from the user. And this method checks to see if this point is on the curve, and we do that by making sure that y squared is congruent to x cubed plus ax plus b in mode p for the y coordinate and the x coordinate of this point. So here we have point g dot get y. You multiply it by itself, so y squared in mode p, if that equal to x cube plus ax plus b in mode p. And this method initializes the domain parameters. So we pick up the elliptic curve by calling this method, and we pick up the generator point from the user, and make sure that that point is on the curve. Otherwise we display this to the user. And here let's define infinity as being this huge number, and the point at infinity has infinity as its y coordinate, and we will have those equals and two string methods. So this returns the x and y coordinates in base 10, and this one in all bases, including base 10, 16, etc. And this equals method checks to see if the past n point is equal to this point, and this should do it for this class. Now going here, let's add this method that checks to see if those 2 points are inverses of each other. So if they have the same x coordinates and opposite y coordinates with respect to the x-axis. And those two methods do point addition and doubling. And those are the equations for point addition, and those are the ones for point doubling. So the x and y coordinates and the slope. And we implement the addition equations here and the doubling equations here. And this method does multiplication using the double and add algorithm. So we do d hops from point G, and we end up in point T. So we turn D into a binary, and we go through each bit in that binary string, and if that bit is equal to 1, then we do an addition after doing a point doubling. And this should do it for this class. So now we can go here and add this method. So we first pick up the private key for this user, and we use it to calculate the public key starting from the generator point, and we send the domain parameters and the public key in a JSON object, and we call the init domain parameters and the calculate public key from this method. And we will have this method that picks up hashes, signs, and sends messages. And we will call it from here. And this method does message hashing, and we call it from this method, handle message hashing. And this is the code that picks up the message and hashes it. And this method picks up the ephemeral key and we will call it from here. And this method picks up the signing key from the user, and those two methods calculate R and S, and this method sends the signed message as a JSON object. So X, R, and S. And we will call those methods from here. So after picking up the ephemeral key, we use it to calculate R, and then we calculate S and send the signed message. So this should do it for this class. Now going here, we will have those two methods. This one to display the calculations, and this one to validate the message. And this one receives the message, so it calculates R and S and W, and it displays calculations and validates the message. And this one obtains the message hash, and we call those from here. So here we are picking up the domain parameters that the other user is using to sign messages. And here we are receiving the signed message. So we call obtain message hash and receive the message. And this should do it for this class. And finally, let's go ahead and test run the application. But before doing that, let's change this. And we will have a server and two clients. And this will be the server, and this is the first client, and this one the second one. So we'll have Alice here, and she will be using SEP 256 K1 curve. So let's copy this. With this generator point. say she will use this secret key, and Bob will use this curve SEP 384. So let's copy this. And this generator point, and let's say he will use this as his secret key. And let's have Alice try to send this message. So she hashes it. This is the hash. And let's say she picks this ephemeral key, and let's have her use a wrong key, so we added 7. So Bob realized that the message was not signed with Alice's private key, so he calculates the hash, and this is the same as the hash for Alice. And then he calculates W, U1, U2, and the point P, and he checks if V is congruent to R in mode N. So now let's do the same thing, send the same message, and same ephemeral key, and this time enter the right secret key for Alice. So here we go. So Bob validates the message, and he determines that it was signed with Alice's private key. And let's have Bob send this message to Alice. So he hashes it, and maybe he chooses this ephemeral key, and his key that he chose was this one. So Alice validates the message and determines that it was signed with Bob's private key. And Eve can see all the communications. So now she has Alice's domain parameters, the curve and the generator point, and Bob's domain parameter, the curve and the generator point, and she can see messages, signed messages originating from Alice and from Bob. And in order to sign any message as originating from Alice or Bob, she needs to solve the elliptic curve discrete logarithm problem and compute Alice's private key D or the ephemeral key of that message, and same thing in Bob's case.